Welcome to the championship final. You have exactly 90 minutes to glory. This is your ultimate game plan for Cambridge Computer Science exam victory. Right now, we're diving deep into the ultimate insider playbook for mastering 4.1 pseudocode constructs. We're talking specifically about the while, repeat, and case structures in the Cambridge IT 9626 exam. But look, listen closely, because the strategies we're unlocking in this explainer today, they apply universally across the entire Cambridge Computer Science spectrum. So whether you are sitting for syllabus 0417, 0478, 2210, 9618, or 9626, you need to hear this. Picture this scenario for a second. It's exam day. You're sitting at your desk. The invigilator just said you may begin. On your desk is a heavily weighted paper and the clock is immediately ticking down. It's high pressure. Let me introduce you to two typical students we see literally all the time in the examiner's room when we're marking these papers. First, there's Alex. Now, Alex is the memorizer. Alex has crammed and memorized every single textbook definition imaginable. But when the exam asks a specific question about evaluating a while loop in a given scenario, Alex completely panics and just overloads the page with raw computer science facts, paragraphs of them. But Alex provides absolutely zero analysis of the actual algorithm printed on the page. Then, on the flip side, we have Sam. Sam is the rusher. Sam's racing against that clock. Sam sees a case construct question, skips right past the specific command word requirements, and just aggressively drops a half-finished trace table onto the page that completely misses the point of the question. And what happens? The examiner's red pen just absolutely strikes through both of their answers. A total red ink massacre. Why? Because neither of them understands the actual strategy. They don't know the game being played. Well, today, we're going to fix that entirely.
So you really have to ask yourself, why do students consistently lose easy, predictable marks on pseudocode constructs? What is going on here? What's really fascinating and honestly a bit frustrating is the massive, fundamental disconnect between what students think the examiners want and what examiners are actually hunting for line by line. When you look at Alex and Sam's flawed answers alongside those glaring red pen marks we just talked about, you quickly realize something absolutely crucial. It is not a lack of intelligence, not at all. It is a complete lack of execution. You see, students find evaluating evidence and drawing conclusions within pseudocode questions incredibly challenging because they treat the exam like a basic memory test instead of an analytical sandbox. They think, if I just define what a loop is, I get points. No. When an examiner asks you to trace a repeat until loop or justify the use of a case statement over deeply nested ifs, they do not just want you to regurgitate the syntax from Chapter 4. They want to see your logical reasoning on display. They want to see you process the constraints of the data right there in front of you. Those red marks on Sam's paper, they're there because Sam didn't prove why the code behaves the way it does in that specific scenario. Examiners are begging you to show your work, show your logic, and connect the dots. We're going to completely rebuild your entire mindset about these specific types of questions right now, from the ground up.
Okay, let's quickly lay out our structured agenda for this session. First, we'll hit Section 1, the assessment reality. Then we move to Section 2, the procedural framework. And finally, Section 3, examiner warnings and pitfalls. By the time we wrap this up, you'll have a rock-solid systematic approach that works every single time.
Let's jump right into Section 1, the assessment reality. We need to completely demystify what actually happens when a Cambridge examiner looks at your test paper. Look, examiners are not just checking boxes on a rubric, they're actively evaluating your cognitive processing. The assessment objectives for 4.1 pseudocode constructs target three very distinct cognitive domains. These are knowledge and understanding, application, and analysis. What this means in plain English is that the assessment framework strongly, almost aggressively, prioritizes analytical depth over superficial breadth. You need to know what a while loop is. Sure, that's your baseline knowledge. You need to be able to actually write one out on paper. Okay, that's application. But here's the kicker. You also need to explain why a while loop is functionally safer than a repeat until loop when you're dealing with an entirely unknown file size. That right there, that is analysis. That's where the big marks live. To achieve this level of analysis consistently, the absolute best students rely on the PEAL framework. Have you heard of this? It stands for point, evidence, explanation, link. You make your point about the pseudocode structure. You provide hard evidence from the algorithm's line numbers. You explain how the logic functions step by step. And finally, you link it all back to the specific context of the user's problem. Trust me, mastering this PEAL framework for computer science is going to completely revolutionize the way you approach these higher mark extended response questions. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Let's break down how this framework maps directly to the expected outputs examiners are demanding. Knowledge requires precise definitions. Application requires causal relationships, meaning you have to explicitly show that if variable x changes over here on line 10, variable y updates over there on line 15. And analysis? Analysis requires cross-topic connections. Let's do a quick interactive check right now. I want you can imagine a 30-second timer on the clock. Consider two different answers explaining a loop structure. Answer A says the code repeats 10 times because of the counter. Answer B says the repeat until construct is utilized on line 45, which ensures the validation check runs at least once before processing the array, preventing a critical null error. I'll give you a second. Which answer rigorously follows our Peel framework and successfully hits that top-tier analysis domain? If you said answer B, you are absolutely right, spot on. It makes a clear point, it uses line 45 as concrete evidence, it explains the underlying mechanics of the post-condition loop, and then, crucially, it links it directly to preventing a null error. That is exactly how you decode command words and extract absolute maximum marks from the examiner.
And to back this up, the crucial point is captured perfectly by the Cambridge examiners themselves. This is a direct insight. Principal examiner reports highlight that candidates referencing cross-topic connections achieve significantly higher marks. So what does this actually mean for you when you're sitting in that exam hall? It means that when you are analyzing a case and case construct, you absolutely shouldn't just talk about the syntax in total isolation. You need to pull back and connect it to other areas of your entire syllabus. For example, you could mention how using a case construct vastly improves the efficiency of a linear search algorithm. Or you could explain how it acts as an incredibly robust validation routine before raw data is actually committed to a back-end database. The examiners are desperately wanting to see that you understand how these specific pseudocode constructs fit into the much wider world of software development and systems lifecycles. This theoretical architecture, this ability to zoom out and see the big picture while analyzing the specific code, is the ultimate secret to moving your paper from a standard B grade straight to an A star.
All right, let's shift gears and move into Section 2, the procedural framework. This is where we take all that high-level theory and turn it into an actionable, point-scoring reality. The absolute key concept you need to internalize here is what we call the method mark strategy. In these Cambridge exams, marks are heavily awarded for displaying a standardized, systematic process. The examiners literally have marks explicitly set aside on their rubrics just for your working out. Remember our students from the beginning, Alex and Sam? Let's bring them back into the picture. We're going to watch how Alex and Sam's disastrous red marks can actually transform into green check marks. We are introducing the computer science success blueprint. Instead of Alex word-vomiting irrelevant facts and Sam carelessly skipping steps, we are going to force both of them into a strict procedural straitjacket. Utilizing correct formats, appropriate terminology, and crystal clear working is an unshakable, non-negotiable requirement. Think about it like this. If you write out a full trace table for a complex while loop, and you meticulously update your variables line by line, column by column, even if you make a tiny, silly arithmetic error at the very end of the loop, you will still secure the vast majority of the method marks. Why? Because your process was sound. The process is literally just as important as the final answer you arrive at.
So here it is. This is the definitive 5-step algorithm you must execute for every single pseudocode question you face. Burn this into your memory. Step 1. Deconstruct the question. You have to ask yourself, what is the specific command word? Is it describe, explain, or evaluate? Those all require totally different answers. Step 2. Extract relevant data. Look closely at the variable declarations and initializations at the top of the code. What are the starting conditions? Step 3. Select your analytical framework. Are you tracing logic through a table? Are you hunting for a syntax error? Or are you comparing two different constructs? Step 4. Execute with clear notation. Write your trace tables neatly using a ruler. Indent your loops properly if you are asked to write out the code. Make it easy for the examiner to read. Step 5. Present with correct terminology. Please do not say the code goes back up to the top. Say the loop iterate. It sounds so much more professional. Imagine giving Alex 60 seconds to rewrite his answer using this exact framework. By simply deconstructing the question in step 1, Alex instantly realizes he only needs to evaluate the specific code provided, not write a 3-page essay on the history of loop structures. This system entirely stops the panic and provides a brilliantly structured pathway to full marks.
Now, zooming in on step 2 of that framework for a second, the extraction phase. Here, you're going to face some highly specific data interpretation demands. You need to actively extract values from complex scenario texts and data tables provided in the prompt. You absolutely must interpret the relationships, for instance, how a specific Boolean flag controls the termination of a while loop, And finally, you must draw rock-solid, evidence-based conclusions about what the algorithm actually outputs at the end of its run. Think about this. If a while loop's precondition is never actually met initially because of the starting variables, the loop never runs, not even once. Recognizing that hidden relationship and writing down 0 iterations occur because the precondition evaluates to false on line 1 is an evidence-based conclusion that examiners literally cheer for when they see it. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's keep this momentum going into Section 3, Examiner Warnings and Pitfalls. This data is pulled straight from the Principal Examiner reports, detailing exactly where the top-tier candidates pull away from the rest of the pack.
The examiners issue a massive alert right here. Candidates consistently confuse key terminology. Let's do a quick mental data scan challenge right now. The biggest, most painful trap students fall into here is confusing a precondition loop with a postcondition loop. A while loop is a precondition construct. It rigorously checks the criteria before it ever runs the code block. A repeat until loop is a postcondition construct. It enthusiastically runs the code first and only checks the criteria at the very end. You must always explicitly define which one you were talking about in your extended responses. If an exam asks why a repeat loop was chosen by the programmer, the specific high-scoring terminology you need is, it guarantees the block of code executes at least once. Do not just vaguely say it's a loop that repeats. Use the precise professional language of a trained computer scientist.
Take a really close look at these top 3 student mistakes, straight from the Cambridge grading desks. Number 1, answers are way too vague. Number 2, forgetting to check format and presentation. Number 3, answers are not specific to the context given. Let's play Find the Flaw for a second. I'm going to read a flawed sample paragraph, and I want you to spot exactly why it loses marks. Ready? The case statement is good because it makes the code faster and easier to read than if statements. It checks the variable and does the right thing. Did you spot the massive flaws in that? The examiner commentary on this would be absolutely brutal. It's completely vague. Why is it faster? What specific variable is it checking? What is the actual context of the program? A top-scoring candidate would instead write something like, the case and case construct is significantly more efficient here than heavily nested if statements because it allows for direct branching based on the value of the menu choice variable, reducing the cognitive load for future maintenance and avoiding deep, complex logical nesting. You see the difference? You have to tie your answer directly to the scenario provided in the exam paper.
Let's visually contrast a superficial, point-losing answer with one that has true analytical depth. The superficial answer totally ignores alternative interpretations. It lives in a bubble. But the analytical depth answer? It uses specific context from the prompt, it uses comparative connectives, and it provides fully justified recommendations. Imagine a 30-second speed writing challenge where the exam asks you to evaluate the use of a while loop for reading a text file. A brilliant comparative connective would be, unlike a for loop which requires a pre-known number of iterations, the while loop is dynamically suited for this specific file processing task because the end of file marker is completely unknown until runtime. Wow. That sentence right there alone demonstrates incredibly high-order evaluative thinking. It compares alternatives, it logically justifies the decision, and it uses perfect context. That is the absolute gold standard you are aiming for.
So to guarantee you hit that gold standard every single time, I want you to memorize this critical analysis checklist. Literally, before you put your pen down and move to the next page, ask yourself these questions. Did I explicitly identify the limitations of the pseudocode? For example, does this case statement handle unexpected user inputs safely with an otherwise clause, or will it crash? Did I expose the hidden assumptions made by the original programmer? Did I thoughtfully consider alternative interpretations, like maybe using a completely different loop structure entirely? And finally, did I analyze how altering the loop condition slightly would fundamentally affect the final output or conclusion? This right here is the ultimate system. We're talking about 3 rules that guarantee top marks. 1. Command word decoding. 2. Rigorous Peel framework application. And 3. A strict time management matrix to ensure you actually have the minutes left on the clock to write this out properly. If you do this, you are mathematically guaranteeing yourself access to the highest mark bands available. I want to leave you with this defining quote. Top-scoring candidates demonstrate evaluative thinking by questioning assumptions, considering different perspectives, and justifying decisions with evidence. This perfectly summarizes the ultimate mindset and the rigorous presentation conventions required by Cambridge. It's really not just about knowing the syntax of the code, it's about evaluating the code's very existence and purpose within the broader system. You now have the complete blueprint. And look,
The proof is in the results. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
So let me ask you one final question. Will you rely on vague, panicked memorization, or will you execute this definitive algorithm for exam victory? The choice is entirely yours. When you open that test booklet and the clock starts, you can either freeze up like Alex and Sam, or you can run the systematic playbook we just covered and dominate the paper. How will you approach your very next algorithm? Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.